Thanks. Pleased to be here. The talk is called HOMFLY PT homology and mirror symmetry, particular 3D mirror symmetry. This is ongoing work with Nick Garner, Justin Hilburn, Alexey Oblomkov, and Lev Ryazanskiy. The basic idea, well, it sort of had two starting points. It was work that Lev and Alexey have done on HOMFLY PT homology, and work that we and other folks have done involving algebraic structures in 3D n equals 4 theories and 3D mirror symmetry. Lev and Alexey have this recent construction of HOMFLY PT homology. It starts out by expressing a knot as a braid closure. And then they introduce this monoidal category of matrix factorization. Where there are elementary matrix factorizations associated to braid group generators. And their tensor products obey braid relations. And then they construct out of this using some machinery. Given one of these braid closures, which translates to some sort of cyclic tensor product of matrix factorizations, corresponding to all the braid generators, they build a sheaf of beta on the Hilbert scheme of endpoints in C2. And what's n? N is the number of strands. Then knot homology comes from HOMFLY homology. Should say the a to the 0 part of HOMFLY homology. Comes as sheaf, as the cohomology of this sheaf in the algebraic sense. So I could write it as hom from the structure sheaf to FB in the category, it's actually a derived category, coherent sheaves on the Hilbert scheme. That's the 0th part. And then to get all of the other A degrees, there's a slight generalization of this.
Derived category doesn't have hom.
It has hom star.
Okay.
Basically, the story is that we understand the essential physics of what's going on.
Categories probably will not come up. I was going to throw them into the end of the talk, but wherever categories do come up, everything in sight is direct.
Okay.
So for other A degrees, This is constructed again as derived HOM from the nth exterior power of the tautological bundle to this same sheaf F beta. And if you're wondering about gradings, so the A degree is coming from this tautological bundle. There are two other gradings that should appear. One is a homological degree, and one is the Q degree. So those are both, well, the Q degree, say it this way, there's a usual standard familiar U1 times U1 action on the Hilbert scheme of points in C2, induced by the U1 times U1 action on C2. And these sheaves are equivariant with respect to this action, which induces a grading on these HOM spaces. There's also a standard homological grading in the derived category, which mixes a bit with these two. So homological and Q are some linear combinations of this and the usual homological grading. Okay. So this is Levin Alexei. Also, last week we heard a talk from Jake Rasmussen. So he and Eugene Gorski and Andrei Negut have a very similar and ultimately equivalent construction of these sheaves, where instead of the starting point is a little different, but you end up with the same object. So instead of matrix factorizations, they use Sergal bimodules. So Rasmussen, Gorski. So I'm going to call this the B side of the story. And in terms of 3D n equals 4 field theory, this translates to the following sort of setup, which I will discuss in more detail in the first half of this talk. This computation of knot homology is actually a computation of a Hilbert space of a certain 3D n equals 4 theory on a solid cylinder. So it's solid. Let's write it. It's d2 times r. The 3D n equals 4 theory in the IR is a sigma model to the Hilbert scheme. So in the bulk, we have a Hilbert scheme sigma model, and there's a boundary condition around the outside which encodes the braid. Finally, to get these tautological bundles, there's an extra line operator. It's going to be a Wilson line threaded along the axis. So one of our goals was to sort of spell this picture out, explain exactly which field theory construction gave their proposal, and Lev had done much of this. In fact, the field theory was his inspiration for writing down the mathematical proposal a few years ago. And I also want to talk about some potential string theory lifts of this, relation to the conifold, and perhaps most excitingly for me, the 3D mirror of this construction. So I call this the B side because the boundary condition and the Wilson line here are all compatible with, I'll call the B twist. There are two topological twists in 3D n equals 4. So side note. There are two twists of 3D n equals 4. Say gauge theories. They often exist for sigma models, but the A twist gets a little tricky. So this is just like in 2D 2, 2. There are two twists, and 3D mirror symmetry swaps them. So there's a duality of some gauge theories with matter that relates them to other gauge theories with matter, if you're lucky, and the twists get swapped. For reference, in sigma models, the Rosansky-Witten twist is the B twist. In pure gauge theory, it was first studied by Blau and Thompson. And that's on boundaries, it reduces to a usual two-dimensional B twist, which is why things like matrix factorizations and coherent sheaves were coming up. The A twist is a reduction of the 4D Donaldson twist. We will not see things like coherent sheaves coming up.
Is that Donaldson-Witten?
Yes.
Donaldson didn't actually twist.
So on the A side, we will be seeing things like vortex moduli spaces and taking de Rham cohomology. Okay. So in the second part of the talk, I want to set up this structure a little more clearly and then describe the mirror. Just in sort of set in words. So very briefly, what we'll find is that these HOMFLY knot homologies should correspond to topological cohomologies of some generalized vortex moduli spaces. This is a new-ish perspective on knot homology, and it's new-ish because at the end of the day, the answer is really closely related to work that folks have done using affine in terms of affine Springer fibers. So, in particular, there's a paper by Oblankov, Rasmussen, Gorski, and Shende that describes torus knot homologies as topological cohomologies of affine Springer fibers, and these vortex moduli spaces are, in certain cases, examples of affine Springer fibers. I'll try to make that connection at the end. Okay.
How about the Cortes commenter and also Zara Smith? Can you?
Well, neither of those have to do with HOMFLY. So one gets those pictures by having a boundary without a bulk. So if we play a similar construction where we just have a two-dimensional theory where some parameters are being braided, then we end up with Kauditz-Chemnitzer on the B side, and I think with Seidel-Smith on the A side, though I'm not 100% sure about that. It would be reasonable to guess that that's what we get. But that's Kovanov homology, or Kovanov-Rosansky, but not HOMFLY. Okay, let me try to relate this to brane constructions and conifolds and such. So I'm going to work up from this bulk theory that I'm sort of claiming is the right thing to look at. If we want to engineer the Hilbert scheme theory as a sigma model, we should start with a gauge theory, a 3D n equals 4 gauge theory that looks like that. The two pieces of data that you need to know to define the n equals 4 theory are a gauge group, which is UN, related to that circle node in the quiver, and a representation, T star R, where R is a copy of the adjoint representation and a copy of the fundamental. So here I'm writing T star because there's this standard but highly compact notation for n equals 4 quivers. A slightly regularized way to write that would be by doubling all the arrows. Sorry, and these are all, I mean, mathematically these are Nakajima quiver varieties. Double the arrows. Then the matter representation shows up as various bifundamental and adjoint fields. There's an x and an I, and in the cotangent bundle there's a y and a j. I think this is just really familiar to maybe 2/3 of the audience and probably completely unfamiliar to the rest. So if there are questions, let me. There's the actual Nakajima quiver variety is the thing that's called the Higgs branch of the 3D n equals 4 theory. So the Higgs branch is a complex symplectic quotient. It's T star R mod GC in the symplectic sense, which means set the complex moment map, which is the commutator of x and y, plus ij to 0, and then quotient by GC. This thing is singular. It should be treated as a stack. If you want to get the actual Hilbert scheme out, should impose some sort of stability condition or some d-term constraint. So a stable part of this, or an open part of the stack, is the smooth Hilbert scheme of n points on C2.
I have a question. Why do you privilege x over y?
It's a great question. I think for this talk I don't really need to. There's a longer discussion about z gradings, and there's some non-canonical choice that gets made, but I don't need to. It's convenient for many things that are totally irrelevant right now. Okay, so the a familiar brane construction of this comes from a Hanani-Witten setup. So in type 2B string theory, we can consider a stack of ND3 branes on one periodic direction that are intersected by an NS5 brane, and did not draw it so that it intersects, but there could be a D5 brane around as well. In terms of the standard sort of forget what these things are called. The table showing which dimensions the branes wrap. So I'll, there's a word for this, right? So I'll have the D3 branes wrapping 0, direction 0, 1, 2, 3. The NS branes wrapping 0, 1, 2, 4, 5, 6. And the D5 wrapping 0, 1, 2, 7, 8, 9. So this, right, why does this engineer the Hilbert scheme theory? We start out with, on the D3 branes, with n equals 4 super Yang-Mills. We put that on a circle, which looks like it should be a 3D n equals 8 theory, which is just n equals 4 with an adjoint. That gives us the x and the y. The D5 brane gives us the extra fundamental hyper. And the role of the NS brane is maybe unappreciated. If we really had the setup on a circle, on a finite-sized circle, the holonomy would be group valued along that circle rather than Lie algebra valued. So if we actually want Lie algebra fields x and y, we have to cut that holonomy with an NS5 brane. Okay, anyway, familiar, I hope. Now, let me redraw this picture a little bit. So here, the x3 direction was going along the circle. Now I'll draw the circle vertically so that x3 is going up. And draw my n D3 branes like this, and then write the x2 direction this way. So why do I want to do this? So here the NS5 looks like that, and the D5 looks like that. I'm not just interested in a bulk theory. In a bulk 3D theory, I want a boundary condition. And if I draw it like this, I can draw the boundary condition. So we can throw in some extra NS5 branes that reduce the number of D3s. And so on. So you can reduce the number one by one all the way down to 0. And so the original NS5 and D5 just go along for the ride. What this ends up giving us is a linear quiver boundary condition that's very, very similar to the T of G boundary condition discussed by Gayotto and Witten in 4D n equals 4. I should probably tell you where the NS prime brane is. So these other branes giving boundary conditions wrap 0 and 1. They don't wrap 2 because that's where things end. And there's some choices. The right one for this sort of supersymmetry is 3, 4, 5, and 7. Okay. So we end up with, in field theory, with something that looks like this. We start out with our Hilbert scheme quiver. And then couple it couple it to a chain of other gauge groups in 2 dimensions. So these are trapped gauge groups, trapped between consecutive NS prime branes. So it goes all the way down to actually 0. Stretching across these NS prime branes, there are pairs of bifundamental chirals. W and Z. And then the rest of the fields that survive just involve a single, not a pair, of adjoint fields on each of the nodes. If I put indices on the Z's and the W's, it would be easier to write what comes next. So I'll call this Wn minus 1 and Zn minus 1. This is Wn minus 2 and Zn minus 2, and so on.
So how do you see that there's only one left?
So you start with 2, and when you start with 2, and you also start with i's and j's for every single one of these, and there are some superpotential couplings involved that simplify the theory. So this is not what you actually get. I could write down something more complicated, and the claim is that it simplifies to this. There's still superpotential couplings involved, but those are difficult to simplify further. So the 2-dimensional gauge group here is a product of un minus 1 times un minus 2 down to u1. The 2-dimensional matter involves the x's and the w's and the z's in appropriate adjoint and bifundamental representations. And purely in 2 dimensions, forgetting the coupling to the bulk, there is a superpotential around that is, from the perspective of the bound, as far as this particular quiver is concerned, this looks like a 2-dimensional 4,4 theory. And there's a canonical superpotential associated to 4,4 theories. That's what I'm writing down just in 2,2 terms. So the superpotential is a sum over nodes of xi times a loop one way minus a loop the other way. So it's wi zi minus zi minus 1 wi minus 1. So W2D is a function to C that's equivariant with respect to the G action. And then the relevant geometric thing, the geometric fact, is that the effective moduli space of this 2-dimensional theory, if we were to write it as a nonlinear sigma model, that's R2D modulo the complexified 2D gauge group. This, again, with some stability condition, is T star of the flag variety for SLN.
But don't you need 2 adjoint if you consider 4.4?
No. There's another adjoint in the vector multiplet. But so the thing I was drawing is the adjoint in the 4,4 vector multiplet. I'm just drawing it as a chiral.
Yeah. Sorry.
Yeah.
Sorry.
So, yeah.
Sorry.
Is this 2, 2 boundary condition?
Yeah, it's a 2, 2 boundary condition. So I mean, the thing is, the bulk theory, because of the framing, only has n equals 4, not n equals 8 supersymmetry. And so this thing is a boundary condition that preserves a 2D 2, 2 subalgebra of 3D n equals 4.
Is it rational like for some general partition?
Sure. It's exactly what you get by reducing the number of branes not by 1 each time, but by some other numbers. It's the same sort of structure that Gayoto and Witten wrote down for 4D superangles.
Does it also have applications?
Yeah, I would hope so. Yes. I mean, sorry, I am sure it does. Very few of them have actually been investigated. Right. So again, for anyone who's not seen this before, why T star flag? The arrows going up are maps from a one-dimensional subspace into a two-dimensional subspace, then into a three-dimensional subspace, and so on. So the flag part is given by the z's. This setting, the moduli space is not R2D stab, it's the critical point, it's the critical locus of W. The modulo of the complex group. Enforcing the critical point equations for W, in part, tells you that the W's parameterize a cotangent fiber to this chosen flag. And so the W's are sitting in the T star. And with the right stability condition, the X's don't do much. Okay. Now, one important geometric thing to say about this is that...
Does that mean they're frozen to expectation values? Is that what
Yes.
Okay.
Yeah, sorry. That's what I mean. So let me say something about the stability condition. Physically, we would not write this as a complex quotient. We would actually write this as dw equals 0, and we would enforce D-term constraints. We would say that some real moment maps for every node were equal to Fi parameters. And then we would divide by the real gauge group. And these Fi parameters are resolution parameters. So here they're n-1 Fi parameters. Ti. The combinations Ti plus I times theta angles for every node correspond geometrically to the complexified Kähler moduli. Of T star flag. So this boundary condition actually depends on these parameters. The real parts, the T's, one can see here as positions in the x6 direction. It's positions of the ns prime branes in the x6 direction. The theta angles are hard to see from that brane construction. In order for the moduli space to actually be a nice resolved space, the complex parameters had better not coincide. So to avoid singularities, to keep the physics in a constant phase, we should not in some appropriate normalization, we should not allow these parameters to coincide. So that describes the theory on the boundary. We actually wanted to use this theory to build a boundary condition. So there's another bit of information I need to tell you. As a boundary condition, we've imposed Neumann for the 3D n equals 4 vector multiplet.
So I'm not exactly sure.
Together with a Lagrangian boundary condition for the hypers. So we'll set, this sets I to 0. It sets y on the boundary to ZW. And there's also boundary superpotential. It's trace of x, ZW. And finally, there's a boundary Fi parameter. Because there's a U1 subgroup of the bulk gauge group that survives at the boundary. There's some complexified boundary Fi parameters. So altogether, we don't just get n minus 1, we actually get n complex Fis, defining the boundary condition. Maybe one other thing to say about this is that geometrically, this combination ZW is the complex moment map for the UN action on the cotangent bundle of the flag variety. And so it's a boundary condition that's setting y equal to the complex moment map. Right. So that's the boundary condition we want. In the B-twist, should I say this? In the B-twist, the n parameters, these n complex parameters, tau I, are irrelevant. So the B-twist in the bulk is also a B-twist in terms of this 2,2 theory. And B-twists of 2,2 theories don't depend on Kähler parameters. So locally, it doesn't matter what they are, but to keep the theory in the same phase, they had better not coincide. And so that means we can braid them around the circle. So if we consider this cylinder picture again, so we'll have the bulk of the scheme theory in the middle, and on the outside, we apply this Bn boundary condition by Bn. I mean that. But it depends on parameters, and we can let them vary. So if I let S be an angular parameter around the boundary, the tau i's can be functions of S. Since they're never allowed to touch each other, they actually encode, as we move around, they encode the positions of strands of a braid. So tau I of S, the vector tau of S, for S and S1 encodes a braid closure. Now, naively, these taus are C-star valued. It is not obvious that that tau I equals 0 makes sense, that's the limit where the real FIs go to minus infinity, and that may or may not be a regular limit. The claim is that here it is. And we'll see it much more easily from a mirror picture or from some other duality frames. Claim is that the TIs are actually, the tau i's are naturally valued in C, not C star. And so this is, if they were valued in C star, then we would be looking at n strands of a braid in C star that are moving around as we change S. And that leads to an affine braid, which is a totally nice thing to study. The point of the framing in this construction is to fill in 0. So if we didn't have this extra D5 brane, we would actually get that affine braid. With this framing, it fills in, and these become C-valued, and we get an ordinary braid in R3. Braid closure in R3, we get a braid on the plane.
Can you say what's happening when one of the taus goes to 0?
I don't have a direct way to say it in terms of, in terms of the flag manifold boundary, that is actually, that does not look good. It's only when you couple it to the bulk that it looks okay, and I can see that by analyzing the Coulomb branch. There's some circle, there's a dual photon in the bulk theory. This boundary condition actually fixes the value of the dual photon to be equal to the theta angle. And then we look at what the Coulomb branch actually looks like, and we see that the circle can shrink. The dual photon circle actually shrinks above some loci, and that's the most direct field theory way I have to see that you can fill it in. And that shrinking is directly related to the presence of this matter. It would not happen if there weren't matter around.
The infinity is still not allowed?
No. Not sure it matters. From the argument I just gave, I don't see any reason infinity would be allowed, but not sure. Okay. There was one final ingredient in the story, which was this Wilson line. So to get other A degrees, we were supposed to insert a line operator in, and that's very easy to describe. So it has to do with a tautological bundle. So if we, good way to draw this, if we can insert a Wilson line, I will just draw it in a stupid schematic way. So what we want is the Lth exterior power of the fundamental representation of UN. That defines a Wilson line in the gauge theory. We can make it supersymmetric by complexifying it. And this Lth exterior power of the fundamental descends on the quotient to the Lth exterior power of the tautological bundle. Okay. Then the claim, as I said before, the claim of Oblomkov and Rosansky is that the Hilbert space of this theory on a disk with all the boundary conditions and decorations added in is the Lth part of HOMFLY PT homology for the knot given by the break closure. Oblomkov and Rosansky don't have a smooth configuration of Fi parameters like this. They discretize things. They assume that the Fi parameters change in discrete jumps, and these jumps correspond to some line operators stuck to the boundary. Their category of matrix factorizations is the category of these interfaces on the boundary. So these are the objects of the matrix factorization category. And it's completely straightforward to read off what this matrix factorization category has to be from the GLSM information I gave. And then they collide these things on the boundary and produce their Hilbert space. Okay. A nice feature of this construction is that the Hilbert space does not just come abstractly as a vector space. It has a natural action of the algebra of functions on the Higgs branch. And this is part way to making it into a sheaf. So this Hilbert space on the disk with a boundary condition that depends on some braid and maybe some line operator. This Hilbert space has an action of functions on the Higgs branch. In other words, functions on the Hilbert scheme. These are the bulk local operators in the B-twist. So think of these as some sort of dots in the bulk that literally act on this Hilbert space. Now, say about this.
For any braid?
Yes, for any boundary condition whatsoever. And so this is a really useful way to produce representations of this algebra.
Rational Daha.
And so here, yes, good. So this is a commutative limit of the rational Cherenkov algebra. And spherical rational Cherenkov algebra. We can introduce various deformations. If the braid is nice enough, if it's something like a torus knot that has some symmetry as we rotate the picture, then we can introduce an omega background and quantize this so that it's not a commutative algebra but a non-commutative one. If we want trigonometric Daha, we should change the matter content in the bulk. So for trigonometric, then T star of the Lie algebra should be modified to T star of the group. And what Satoshi and Sergey and Ingmar and Peter have been studying is a Daha version of this, which I would say appears most naturally on the mirror side, without a framing node. So these pictures have appeared in many places, including including in the work that these guys have been doing. They appeared when we were trying to understand symplectic duality and modules for Higgs and Coulomb branch algebras. But this is a completely general way to build modules for these algebras. Great. Yes, I'll stop. That's enough for the B-twist. Let me move on to dualizing the picture a bit and maybe move a little bit faster. So we can T-dualize from 2B to 2A by compactifying on the obvious circle. That's the X3 direction. We'll we'll get D2 branes immersed in a D6. So the D3s become D2s, the D5s become a D6. 2, 3, 7, 8, 9. The NS prime branes stay NS prime branes. And there's a small additional complication, an interesting additional complication, since we're T-dualizing transverse to an NS5 brane. What we actually get is Taub-Nut, where the Taub-Nut circle is the X3 direction, and then that's fibered over direction 7, 8, 9. From a complex geometric perspective, we can just think of Taub-Nut as C2. In some limit, this becomes a flat space. So here, it's much more obvious that we're supposed to be looking at something ADHM-like, that we get the Hilbert scheme. There's a D2 brane embedded in a D6, which is Witten's construction of the ADHM moduli space. Now, this then, at least schematically at this point, is related to the conifold. So we can do a lift to M theory. We should recall a few things. So the Oguri-Vafa setup on the resolved conifold side, it's the following sort of thing. So we look at O minus 1 plus O minus 1 over P1 with a toric diagram like that. And if we want to produce HOMFLY polynomials out of this, or HOMFLY homology by counting BPS states, we should add a few extra ingredients. First, there's some M5 brane that represents the knot on the resolved side. And then for knot homology, one is counting BPS states of M2 branes that look like they wrap a cigar ending on that M5 in the presence of some other M2 branes that wrap the P1. And I hope that's a familiar construction. Should call this M5 prime. So the schematic idea is to reduce to type 2A in a neighborhood of a pole of the P1. To sort of zoom in on that part of the picture. So over the North Pole, we'll view O minus 1 plus O minus 1. I mean, the bundle is trivial here. Over close to the pole, it just looks like it's over C. We want to view this as Taub-Nut plus C over C. And reduce on a Taub-Nut circle. Now, what is the difference in the two copies? So I specifically want the M2 branes to wrap a disk inside the C that's not doing anything at all. So that's something bad. Okay, so this copy of C contains a disk of M2 branes, or cigar of M2 branes, ending on some M5 prime. And then the vicinity of this pole reducing on a contractible circle takes us to type 2a with the following features. The fact that the circle is contractible throws a D6 brane into the geometry. The M5 brane doesn't change dimension. It becomes an NS5 brane. The M2s become D2s. And here we're getting sort of the flat space limit of that other tau knot. So the claim is that this, in the neighborhood of a pole, reproduces that construction. A nice feature is that the M2s, which become D2s, are already wrapping a disk. We're already in the solid cylinder setup. There's a time direction just in the non-compact space that I'm not saying anything about. And so we already have a solid cylinder. Moreover, these other branes become fundamental strings upon reduction that just sit at the origin of that disk, and that's the line operator. So that's at least the conjectural relation to the conifold. So to answer a question that came up last week, why is there a Hilbert scheme around? It's coming around because of D2s immersed in this D6 from the reduction. Okay. So that's one duality. Do a few more.
So why is it the antisymmetric?
Sorry?
Was it the exterior power
of because I think if we have L fundamental strings, it depends whether the fields on them are fermionic or bosonic, and with the right setup, they're fermionic fields, and they'll produce.
They're bounded by n.
They are. Right, sorry. So where does n come in? I didn't actually say here. So the sort of knot we want is a very tight braid. So if we just had a single M5, that would produce an unknot. And we sort of want an n-fold wrapped M5 that actually sweeps out some interesting braid closure. And then these disks are not singly wrapped disks. They sort of go n times around, and so these are actually n M2 branes. Hence, we're getting n instantons. And these other red M2s that are sitting on P1 are intersecting like all of these things at once. So the claim is that a single fundamental string intersecting all of these at once produces a fundamental representation of the GLN gauge group. And L fundamental strings behave fermionically and give the exterior power. There's a nicer brain construction of this Wilson line where analyzing the supersymmetries is a little bit easier, and one can actually see the exterior powers coming up. I think there are details of the conifold construction that still need to be worked out carefully. That would be the idea. Okay. So then let's dualize further. So we started with some type 2b D3 NS D5 system with some NS prime branes giving boundary conditions. We T-dualized this to type 2a, and then we lifted that to M theory to a conical geometry. So in type 2a, there was a D2 immersed in a D6 sitting in tau nut with, again, NS5 boundary conditions. Now we can apply S-duality to get to a 3D mirror. So S-duality takes us to a dual type 2b theory where the roles of the D5s and NS5s swap. And then we can do the same thing, apply T-duality to go down to some dual type 2a configuration that again has a D2 immersed in a D6, but now has D4 prime boundary conditions. So I want to sort of draw that a little bit. It looks like this. So we have some ND2s that are cut by a D4 prime into N minus 1 D2s, and so on. So the number is reduced in the same way as before, but now by D-branes, all the way down to 0. And the whole thing is immersed in a D6 background. Okay. This is actually a much nicer boundary condition to study. And it should be familiar from work of Gayotu and Witten what it is. It is a pure Dirichlet boundary condition on the gauge fields with no nonpole, no singularity, that just fixes the values of some of the hypermultiplet matter fields. So to spell things out, so in the 2a tilde picture, so this is the 3D mirror. The bulk theory is still the Hilbert scheme theory. But the Higgs and the Coulomb branches have been swapped. So our original Hilbert scheme is actually the Coulomb branch. Some very brief things to say about Coulomb branches. So in general, there's a fibration. So the Coulomb branch is a complex integrable system over the complex torus of the gauge group. Over the complex cartan of the gauge group mod vial, whose generic fibers are dual tori. What that means for us, the gauge group is GLN. So this Coulomb branch is a complex integrable system whose base is just Cn, and whose generic fibers are C star to the n. And these shrink at some points. So there is a parameter around, there's a mass parameter in the theory that I don't want to talk much about. But for the right value of that parameter, this really looks like this. Looking at functions on this, you just get the symmetric product. So everything, all of the C star fibers shrink at 0 in the base. And this space just ends up looking like functions on MC look like functions on C2 to the n mod vial. And then if we're careful about what's actually going on at the origin, we'll see that this gets resolved into the Hilbert scheme. Great. There's a Braverman-Finkelberg-Nakajima construction of the Coulomb branch algebra much more explicitly as the cohomology, this topological cohomology of some infinite dimensional space that looks sort of like the affine Grassmannian for GLN, enhanced by the representation. I will maybe say a bit about this at the end, but this sort of construction involving the affine Grassmannian is going to tell us that the Coulomb branch algebra acts naturally on the cohomology of the moduli spaces we'll build by convolution. Okay, so now let me get back to the boundary condition. If I drew one of these little tables of dimensions, which I don't think I'm going to take time to, we would find that these D4s localize exactly half of the fields here. In particular, they fix X but not Y. So what's the dual of this boundary condition? It's so on the gauge fields, so it's pure Dirichlet. In other words, it breaks gauge symmetry completely. And it sets X at the boundary equal to something fixed. And it sets Y at the boundary equals to something fixed. And these fixed things are up to us. They're determined by the geometry. In particular, they're determined by the positions of the D4 prime branes. The invariant data here, modulo sort of constant gauge transformations at the boundary, sits in the eigenvalues of X. So in particular, this boundary condition depends on the eigenvalues of X at the boundary. Lambda 1 through lambda n. And these are precisely mirror to the complexified Kähler moduli on the other side. So something rather cool happens. We had this really complicated boundary condition that involved coupling to a flag manifold, and it's been turned into something extremely simple, where we don't need to talk about resolutions. We just have fixed eigenvalues for this field. And in the same way, in order to keep the boundary condition in the same phase, we should not let these eigenvalues coincide. When they coincide, the stabilizer under the gauge group of this element will jump. And so the condition is that the stabilizer is trivial, and that makes these be distinct. Great. So now let's put this on a cylinder. We can do exactly the same thing as before. So we now have this dual Hilbert scheme theory in the bulk. Eventually, we will want to look at the A twist instead of the B twist. And there's a dual boundary condition that's Dirichlet. Right, so this boundary condition depends, literally in terms of the data, it depends on some x at the boundary and some I at the boundary. And we can let that data vary as we sweep around. And the eigenvalues will sweep out a braid. So the eigenvalues, lambda of s of x, define a braid. So then, and the Hilbert space of this thing, Hilbert space on D2 with data, should be the L equals 0 part of HOMFLY homology. We can insert a line operator in as well. Let me just say briefly what the mirror map does to the line operator. So there's a really nice paper of Essel and Gomez that realizes line operators and quiver gauge theories through a Hanani-Witten type brain construction. And then one can map the fundamental string that gave the Wilson line, fundamental strings, into some D1 brains that are going to produce a vortex line. For the vortex line, there are many ways to define it. One is by specifying some singularity in the x fields. Another way is by saying how the theory is coupled to 1D quantum mechanics. So this is just like the definitions of Guyot-Witten surface operators in 4 dimensions. There's sort of an IR definition and a UV definition. The UV one is actually pretty easy. The line, so the vortex, corresponds to coupling to 1D, n equals 4 quantum mechanics, with a quiver that looks like this. So this is n equals 2, 2 type quantum mechanics. The moduli space of the quiver is n copies, I think, is n copies of the tautological bundle over the Grassmannian of L planes in n space, which is a space that is really, again, shows up over and over and over again in knot homology. This is the tautological. Maybe I'll call it tau again. Okay, whatever. So one can couple the bulk theory to this thing by gauging the diagonal un in the coupling and adding some superpotential, which I am loath to describe right at the moment. I want to say how you actually compute some things. This Hilbert space, physically, shows up as the Durham or Durham-like cohomology of a moduli space of BPS equations on the disk. It's time-independent BPS equations in the A-twist in this geometry. And those things are what I was calling vortex equations. In general, so for the 3D n equals 4 theory, with group G in matter R, the moduli space of BPS configurations on the disk takes the form, if we complexify the gauge group and write everything in algebraic, at least holomorphic language, this ends up being a space of holomorphic GC bundles on the disk with a choice of section, the holomorphic section S. of an associated T star R bundle such that the complex moment map vanishes. So it's this modulo complex GC gauge transformations. And one might hope then to compute this in an algebraic model, which algebraically we don't say holomorphic, we just say GC bundle. Yeah, GC bundles. On some suitably algebraic version of D2, there are choices with sections S such that mu of S is 0. Mod, just algebraic, sorry, this was mod holomorphic gauge transformations. This is just mod algebraic gauge transformations. Okay. So yeah. Let me plan the next few minutes for a second. Wanted to actually give an algebraic definition of the space and then compute something. I need to say how the boundary condition shows up. Let me write down some algebraic data. So what do you do with the boundary condition? So the Hilbert space on a disk is going to be cohomology of this. So Hilbert space on D2 is cohomology of this MD2, but it's not this MD2 with free boundary conditions. It's some decorated version of MD2 with appropriate boundary conditions and maybe a singularity at the origin corresponding to this vortex. So I want to say what the boundary conditions are, at least one version of them. Right. So given a braid closure, I want to choose an X on the boundary sitting in n by n matrices whose entries, loosely speaking, you would expect something like polynomials in Z and Z inverse. If we're working on the boundary of a disk, then holomorphic sections there, functions on a neighborhood of the boundary of a disk, look like polynomials in Z and Z inverse. If we put the disk, if we make the disk very, very large, so that we're sitting very close to the point at infinity, we might also allow ourselves to work with formal series expanded around infinity. And I will actually do that for the proposal. So X is an n by n matrix whose entries are formal Laurent series in Z inverse. So these are things like Z to some power, starts with a polynomial and then has a Laurent series thrown on. Has a series in Z inverse thrown on. Okay. So given a braid, we want to choose such a matrix such that the eigenvalues make sense. Not in a formal neighborhood of infinity, but in an actual neighborhood of infinity. So they make sense at, for example, Z equals 1. And define the braid. And there's some data that goes into choosing a compatible I. So we'll choose an I on the boundary, that's in the same sort of thing. So it's C of Z inverse to the n. And the choice is not very important. The only thing that it needs to satisfy is that the stabilizer of x delta and I delta under the gauge group at infinity is trivial. This is to break all gauge transformations. Great. Y and J don't do much. They are around, they're not fixed. And when we take cohomology, nice example is we'll do it with a fixed point calculation in which Y and J are just 0. Otherwise, Y and J end up being part of some infinite dimensional vector bundle over the space we're looking at. But they, as far as I can tell, they don't seem to play much of a role. So let me just proceed with X and I.
What do you mean define braid?
Well, so it's the same picture that I've been drawing. So the eigenvalues evaluated on the circle are going to be the positions of n strands. So there are n different eigenvalues, and these are complex numbers that tell you where the strands sit as we move around the circle of the braid.
There is a slight logical problem in what you've written, because you were given beta tilde at the beginning and then you defined it.
Oh, are compatible. I mean, no, sorry, I didn't mean define.
They reproduce.
Yes, reproduce. Thank you. Great. Example. If we have an unknot on n strands, if we have an unbraid on n strands, so when we close this up, we'll get n unknots. Then X can just be taken to be a constant matrix with n distinct eigenvalues, which are the positions of the strands, and we want to choose any I that kills gauge transformations, and we can just make it a constant vector of ones. A more exciting thing, mildly more exciting thing, is to consider a 1 over n twist. And then, so this actually closes up into just an unknot. And then X can be chosen to be a matrix with a bunch of ones below the diagonal and a single Z in the corner. And an I giving trivial stabilizer looks like that. And we can tell that this corresponds to that braid by looking at the spectral curve. So determinant x delta minus lambda is just z to the n minus lambda. Sorry, it's z minus lambda to the n, which tells you that the eigenvalues, going around the unit circle, the eigenvalues are just going to be the roots. And I'll sweep that up.
What is lambda here?
Sorry?
What is lambda?
It's the eigenvalue.
Nothing to do with
This is telling you what the eigenvalues are as functions of z. Yes.
Is it clear that there's such a choice? I mean,
No.
for any braid.
So no, and if we stick to, in fact, it's clear that there isn't if we stick to polynomial matrices.
Sure.
So if we look at matrices valued in polynomials in z and z inverse, the only things we'll get are the knots corresponding to plane curve singularities defined by the spectral curves. I would hope that working more generally over series, one can get other knots, but it is not obvious. It's sort of not. It's.
It's not known, but it might be obvious.
Yeah, thanks. It would be nice to have a proof of this fact. I don't know. It's not. Yeah.
So you said formal power is formal Laurent series, right? But then you have
Yeah, I mean power series, but that makes sense in a neighborhood. So it's not all formal. I mean, you really do need these to make sense in a neighborhood of
So
infinity.
you do mean converge.
I mean convergent, but there's a lot of space between polynomials and convergent power series.
Yeah, for sure.
Sure.
So yeah, that's so yeah. I mean, it feels very similar to the problem of taking an arbitrary real loop and analytically continuing it. So the braid is an arbitrary loop in it's an arbitrary element in the real loop space of the representation, and we're trying to find some algebraic representative of that, which I am hopeful exists, but not sure.
Anyway, you can get a lot of interesting knots this way, and
Yes.
hopefully all.
Yeah, I'll finish up. Can get a lot of interesting knots. The space we're looking at then is the following, and I'll do the version without a vortex. So let K infinity be this formal Laurent series ring in Z inverse, and let OD be just polynomials in Z. So there's a group of gauge transformations near infinity, G of K infinity, which is just the complex group defined over that. Sorry, I'm going to be quick. So similarly, there's a G of OD, which is just polynomial valued gauge transformations near the origin. Well, that makes sense in an actual disk. And we want to do the following. So we'll start out with our X and I on the boundary. We'll take their full G of K infinity orbit and then intersect with polynomial valued X and I. In other words, we want sections that extend smoothly over the origin. And to implement the constraint that they extend smoothly over the origin, we'll intersect with polynomials. And then we can divide this. So we want to quotient out by gauge transformations near the origin, which is G of OD. So this defines a genuine space. So it's M beta 0. And the conjecture is that the topological cohomology of M0 beta is the HOMFLY homology. Closure beta in A degree 0. And it is fun and easy to actually verify this for things like unknots or for these simple twists. So the past few weeks, Nick has been working out examples of this. And I wanted to go through one, but I'm out of time. So I'll be a mathematician and end with a definition and no examples.